Hello, everybody. This is Sunday, October 23rd, and we are moving into Module 9 of our online astronomy course. That means we're starting the section of the course on the stars. And we're going to start with our star, the sun. But before I tell you a little bit about the sun, I want to remind you that next week, that is starting tomorrow on Monday, the exam number 2 opens up for you to take it on Canvas, just like you did exam 1. And you have from that Monday, which is October 24th, all the way to Sunday, October 30th, to finish it. 35 multiple choice questions, very much like the last one was. You can use your book, you can use your homework quizzes, but no other resources are allowed. You're welcome to have a calculator handy, but you're not going to need it. So I wish you all good luck on that. And I'll also be sending out an email today, just letting you know that that's coming. Okay. Module 9 is about our sun. It's the one star that's close to us. And what can I tell you about the sun? Well, first of all, it is huge. I mean, look at the picture behind me. This shows the sun behind me. That's a solar flare going off, hot gases that are caught in the sun's magnetic field. And right here is Earth. And so you can see that Earth, compared to the sun, even compared to the size of these flares and prominences, Earth is quite small. In fact, if you hollowed out Earth, made it hollow, I'm sorry, let's try that again. If you hollowed out the sun, made it hollow, you could drop 1 million Earths inside, one by one. Over 1 million Earths would fit inside the sun. So you see it here, it's a hot, glowing ball of gas. The sun has no solidity to it, no liquid. It's gaseous all the way through. And what gases? Well, 71% of the sun's mass is hydrogen. Another 27% is helium. That means that only 2% of the sun's mass is made of heavier elements. Sun is also bright, hugely bright. In fact, the sun gives off energy per second of 4 times 10 to the 26 watts. That is the same as, let's see, 4 million 100-watt light bulbs shining. So that's just ridiculous amount of energy. It's enough to power in 1 second. The sun gives off enough energy to power Earth's current energy needs for 800,000 years. What else about the sun? Well, where does it get its power? What's powering the sun? Is it burning like coal is burning, like wood might burn? And the answer is no, not at all. The sun is powered by nuclear fusion reactions. And the main one is called the proton-proton chain because it's a chain of reactions that changes. What goes into this reaction are 4 protons. 4 protons go into the reaction, and ultimately they fuse all together. And what comes out is 1 helium nucleus. Now, a proton is just a nucleus of a hydrogen atom, and so the sun is converting hydrogen into helium at a tremendous rate. In fact, for every 1,000 kilograms, for every 1,000 kilograms of hydrogen that goes into that equation and fuses together, there's only 993 kilograms of helium that comes out. So where did those missing 7 kilograms go? Well, you've probably heard of Einstein's famous equation E equals mc squared, which says that mass, m, can be changed into energy, that's the E, and the conversion factor is the speed of light squared. Now, you know the speed of light is 3 times 10 to the 8 meters per second. So that's a large number. So squared, it's even larger. And so a little bit of mass can be changed into an awful lot of energy. And in fact, the sun is converting almost 5 million tons of its mass into energy every second. And you might think, oh my gosh, our sun is going to run out of energy. Well, yes, it will, but it's been going for about 5 billion years, and it has another roughly 4 billion years to go. And later in the course, we'll see what happens to stars as they run out of their nuclear fuel. Now, in the center of the sun, the energy is released in the form of photons. Remember that photons are the massless particles of light that carry the energy and momentum of light. So these very energetic photons are created in the sun, and they can't stream right to the surface. They bounce around. They bounce, they hit a nucleus, they bounce in one direction, hit a nucleus, they bounce in another direction, hit a nucleus, bounce in another direction. And eventually they sort of random walk their way out of the sun. And it takes about 1 million years for that light to reach the surface. And so if you go outside and you feel the sunlight hitting you, know that that light was created around 1 million years ago in the sun's center. So those photons make their way to the surface. You can tell it's not a very efficient process. In fact, it's so inefficient that the outer 30% or so of the sun is undergoing convection. Now, convection is just hot gases being buoyant and rising. They carry their energy upwards, they cool off, and then they fall back down again because cool gas falls, and they are reheated and again carry energy to the surface. So this boiling motion is what carries energy to the surface. Now, our sun, the visible surface of the sun, what you're looking at here in this picture is called the sun's photosphere, because that's where the photons that reach our eyes comes from. Above that, there's a chromosphere. Chromo means color. And if you look at the sun during a solar eclipse, you'll see this red layer, this thin red layer around the sun. It's really cool looking. And finally, there's the corona, the sun's hot corona, millions of degrees hot, and that emits X-rays. So we can study the sun in X-rays too, besides just looking at it in visible light. Now, every once in a while, there's a dramatic flare, like this one that you see behind me here. What happens is that flare can release a lot of charged particles, protons, electrons. And if those come toward the Earth and hit the Earth, they cause aurora. Those charged particles follow Earth's magnetic field lines, and they cause aurora in our atmosphere. They can also cause havoc with our electrical grid and satellites that might be orbiting. By the way, I should point out that fortunately for Earth, this is not to scale here. Right? The distance between Earth and the sun is much, 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 much more than that. So we're not like we're just roasting over the barbecue. So that is just a little bit about our sun. It is fascinating. It's the one star we can view close up. And really, we've even sent something called the Parker Solar Probe. There's a video about that in this module. And it came from Earth, it looped by Venus, and it uses Venus's gravity to slow down enough that it can come close to the sun, and it's actually diving through the sun's atmosphere. It moves very fast. It's the fastest moving spacecraft ever launched, and that allows it to survive the passages through the sun's atmosphere. Well, before I leave you, let me pull up Stellarium. There we go. Just a second. I need to do that differently. There we are. There's Stellarium. I don't know why I did it some strange way, but it didn't work. But here's Stellarium. And you can see that you're facing north. This is actually tomorrow. So this is Monday at 9 at night. And you can go out and look north. You can find the Big Dipper. And if you haven't found the Big Dipper yet, I hope you will go out and see it. Now, with clouds covering northern Utah, tomorrow night might not be the best choice. But if we go forward a couple nights, here is Tuesday. Tuesday, by the way, is the day of the new moon. So we're starting a new cycle of lunar phases. Here's Wednesday, Thursday, Friday, Saturday. And you can see that as time goes on, now we're into November. But there's plenty of time you can have to see the Big Dipper. In fact, it's a circumpolar constellation, which means that it's always visible any time of the year. And right now, it's nearest the horizon. So take a look at that. And I hope you have good luck on your second exam. As always, if you have any questions, you can email me. I'll be happy to set up a Zoom meeting with you, or you can meet in my office. Always happy to see people. So good luck on the exam, and I will look forward to seeing you next time. Bye-bye.